This is the pencast for section 4.1.2, Homogeneous Equations. So in order to make sense of what a homogeneous equation is, and in particular a homogeneous linear equation, we need the following definition. We will say that an nth order linear differential operator is an operator of the form a sub n of x times the nth derivative with respect to x plus a sub n minus 1 of x times the n minus first derivative of x, and so on down to a sub 1 of x times d dx plus a naught of x. And so notice this is an operator. So this is going to eat a function and it's going to return some other function. So writing a differential equation or writing a differential operator in this way allows us to make the following two definitions. Namely, we can write an ordinary differential equation as a linear nth order operator evaluated at a function y equals 0, and that kind of differential equation we would call homogeneous. Or we can say L of y equals g of x, where g of x is some non-zero function, and that is a non-homogeneous differential equation. So in this section, we're going to be interested in the first type, the homogeneous differential equation. Roughly speaking, this is the right-hand side, quote unquote, equals 0. So the linear differential operators have several properties that you should read about in your notes. Namely, they are linear, and you should recall or read the precise definition of what that means. And also, they obey the property of superposition, which follows from the fact that they are linear. So make sure you read about that. What we're going to be interested in this section is defining a set of fundamental solutions. So if I have an nth order differential equation, in general, I am going to have n linearly independent solutions. And so we're going to want to try to find out when I have such a set and how to recognize that a given set of functions is one of these fundamental sets of solutions. So to get there, we need kind of a number of definitions. I'll make a note that if you've taken linear algebra, you've seen some of these definitions before. So the first is, let's say I have a set of functions, f1 through fn. We will say they are linearly independent if whenever I can write the equation of the form c1 f1 plus c2 f2 plus cn fn equals 0. So here my c sub i's are just real numbers. So if I can write down that equation, which I'll call star, that must mean that all my c sub i's are equal to 0. So in other words, the only way I can write equation star is if all of the constants in front of my functions are equal to 0. That's what it means for a set of functions to be linearly independent. The converse of that is that we have a set of functions are linearly dependent if there exists a set of real numbers that are not all 0 such that my equation star holds. So in other words, I can do c1 f1 plus c2 f2 plus cn fn equals 0, and not all of those ci's are equal to 0. Then we say my set of functions are linearly dependent. And we'll talk a little bit in class about what that means for a given set of functions if they are linearly dependent. So let's suppose that I have a set y sub 1 through y sub n of linearly independent solutions of an nth order homogeneous linear ordinary differential equation. And I wrote nth in red here because that is the same n as the number of solutions in my set. That's really important. So if I have that, then we say that this set is a fundamental set of solutions. Another way that you might think about this, excuse me, if you've taken linear algebra, is that the set y1 through yn forms a basis of our solution space for this ordinary differential equation. If you haven't taken linear algebra, well, this is just a precursor or preview of what's to come in linear algebra. So we'll call these a fundamental set of solutions. Now, let's suppose that I have n functions and they all have at least n minus 1 derivatives. Then the Wronskian is a functional, is what it's called. So it eats a set of functions and returns whoops, sorry, I totally misspoke there. The Wronskian eats a number of functions and returns another function. Sorry about that, not a functional, just a map from a set of n functions to a single function. And what is it? It is the determinant of the matrix that is shown here. So I take the first row of my matrix to be my n functions. The second row is the first derivative of the n functions, and so on. And then the last row is the n minus first derivative of the n functions. And those straight lines on the side of the matrix say take the determinant. And it's going to turn out that the Wronskian is going to help us determine if a set of n functions is a fundamental set of solutions. So here are two theorems. We're not going to prove them in the video. We'll talk a little bit about the proofs in class. So if I have a linear nth order ordinary differential equation that is homogeneous, so written L of y equals 0, then there exists a fundamental set of solutions to that differential equation. So there exists a set of n linearly independent solutions. And if I have a set of n linearly independent solutions, in other words, if I have a fundamental set of solutions to an nth order linear ordinary differential equation that is homogeneous, then we can write the general solution as what we call a linear combination of my n solutions, of my n fundamental solutions. Namely, the general solution is y equals c1y1 plus c2y2 plus ... cn yn, and the ci's can be anything. So that tells me for a given ODE, if let's be precise here, a given nth order linear homogeneous ODE, if I have a fundamental set of solutions, then the most general solution can be written as a linear combination of those. And again, if you've seen some linear algebra, this should not be a surprising fact. So how do we know if I have a set of n solutions to a differential equation? How do I know if they are linearly independent? Well, that's where the Wronskian comes in. So a set of functions is linearly independent if and only if the Wronskian is non-zero. So that's going to be, if we're given a set of solutions, that's how we're going to determine if they are linearly independent. So let's see an example of that. The two functions, y1 equals cosh of 2x and y2 equals sinh of that should have been sinh of 2x. Let me fix that. Sinh of 2x. Solve y double prime minus 4y equals 0. And remember, cosh and sinh are hyperbolic cosine and hyperbolic sine, and you can check that they solve this differential equation. I would like to know, is this a fundamental set of solutions? So the first thing, we need to make sure we have the right number of solutions. This is a second order differential equation, so a fundamental set of solutions would have two solutions. Okay, so we're good there. And then the next thing we need to check is, are these two solutions linearly independent? So let's compute the Wronskian. In the first line, we write cosh of 2x, sinh of 2x. Then we take the derivative of each, so we have a chain rule, and remember the derivative of cosh is sinh, derivative of sinh is cosh, so the second line, the second row becomes 2 sinh of 2x and 2 cosh of 2x. Then we take the determinant of that matrix, and you may need to review how to compute determinants of matrices, and we get 2 cosh squared of 2x minus 2 sinh squared of 2x, and using trig identity or hyperbolic trig identity, that cosh squared of anything minus sinh squared of the same thing equals 1. We get that this equals 2, which is not 0. So we conclude that indeed y1 and y2 are a fundamental set of solutions, or form a fundamental set of solutions. So by our theorem that we talked about earlier, we can ultimately conclude that a general solution to this ordinary differential equation is y equals c1 cosh of 2x plus c2 sinh of 2x. And we'll talk a little bit more in class about the proofs of these various theorems, and we'll talk a bit more about the why behind this. Why are we interested in finding general solutions?